Hello, my name is Silva, and I am a researcher here at Instituto Superior Técnico in Lisbon. I'm going to present the paper Influence of Carbon Dioxide as a Mixture Component on Cement Hydration. Regarding this presentation, I'm going to start with a brief introduction on the subject, talk about the materials and methods used, present the results obtained, and finally draw some conclusions. Cement production has documented by several papers. It has a high environmental impact, mainly due to the release of CO2 during the processes of calcination of limestone and combustion of fuels. However, during the concrete surface life, there is a CO2 uptake of concrete in a process named natural concrete carbonation. Besides this natural reaction, recent papers have focused on the carbonation curing of precast concrete structures, providing an additional CO2 uptake. On this paper, we focus on using CO2 as a mixture component with the objective of ensuring a CO2 storage in concrete structures. Regarding the materials used, in this paper was used cement type 1 and carbonated water, being this carbonated water a mix of distilled water and CO2 with about 100% purity. The precarbonation of the mixing water was achieved using an airtight chamber with a CO2 supply which was connected directly into the water. The water was initially fully carbonated by providing an atmosphere of 80% CO2 for 20 minutes. Preliminary tests indicate that the pH of the water stabilized at 4.3 once it reached the 20 minutes of carbonation, indicating fully carbonation of the water. Once the water was fully carbonated, the CO2 was cut and the door of the chamber was opened and closed, ensuring the removal of all the CO2 in the chamber atmosphere, thus returning to the initial chamber atmosphere. This imbalance between the carbonated water and the chamber environment leads to the release of CO2 by the carbonated water, which was measured by the CO2 sensor. Thus, based on this plot of gauges CO2 concentration in the environment chamber over time, we were able to define 3 levels of carbonated water based on the waiting time before the usage of this water. The first, a high carbonated water with the shortest waiting time. The second, a medium carbonated water with a longer waiting time. And finally, a low carbonating water with the longest waiting time. Finally, the CO2 concentration of each carbonated water was estimated based on Henry's law. With these different carbonated water, samples with a water-cement ratio of 0.5 were made and cast into prismatic molds. With the resulting prismatic specimens, several tests were made in different curing ages. The tests made were compressive strength, pH measurement, X-ray diffraction, and finally scanning electron microscopy. Regarding the compressive strength test, the results indicated an increase in compressive strength for the samples with a curing age of 3 days. This first result seems to indicate an acceleration of the hydration reactions caused by the presence of CO2 in the carbonated water. However, for the following ages, there is an inversion of this trend. For the samples with carbonated water, there is a reduction in the compressive strength when compared with the reference sample. To further investigate the influence of carbonated water, an X-ray diffraction test was performed, focusing on 4 different compounds: halite, B-lite, calcium carbonate, and calcium hydroxide. First, focusing on halite, for the curing age of 1 day, there is a higher consumption of halides in the carbonated samples, for both high and low carbonated samples, when compared with the reference sample, indicating that the presence of CO2 in the mixing water seems to accelerate the dissolution of this compound and consequently the hydration reactions of cement. However, for the following curing ages, the results indicate a similar quantity of halide for both the reference sample and the carbonated samples. Concerning B-lite, there is not any substantial difference between the carbonated and uncarbonated samples for any curing age. For, for calcium carbonate, there is a slightly higher quantity of calcium carbonate for the carbonated samples for both the high and low carbonation level for the curing age of 1 day. For the subsequent curing ages, the calcium carbonate seems to have a similar quantity. Regarding calcium hydroxide, there is a similar quantity in every curing age for both uncarbonated and carbonated samples, indicating that the CO2 present in the carbonated water was not able to carbonate all the calcium hydroxide produced during the cement hydration reaction. For scanning electron microscopy, only the reference sample and the high carbonated sample were tested for the curing age of 3 days. For the reference sample, there is a presence of cement hydration products with a bigger dimension on average than the high carbonated sample. There is also a presence of needle structures, presumably intrinsic. For the high carbonated sample, the presence of these needle structures was also detected, but in a lower amount, being also identified calcium carbonate compounds using AGS. Concerning the pH measurements for the reference sample, there is an increase of the pH value throughout the curing age as expected, stabilizing at the value 12.7. For the low carbonated sample, there is an increase in the pH at the early ages, 3 and 7 days, and also stabilizing at 12.7 for the later ages. Regarding the medium and high carbonated samples, the pH value also stabilized for the later ages at about 12.7, indicating an absence of the durability problems usually associated to the carbonation process in concrete structures. Another result from this test is the decrease in the pH measurements when the amount of CO2 in the carbonated water increases for the early ages. This result can be explained by two mechanisms. On one hand, there is a higher dissolution of halite shown by the X-ray diffraction test, which increases the presence of calcium hydroxide in the liquid phase, increasing the pH value. On the other hand, the presence of CO2 in the carbonated water consumes the calcium hydroxide in liquid phase, decreasing the pH value. Therefore, the low carbonated sample appears to have enough CO2 in the carbonated water to promote the dissolution of halite and acceleration of the hydration reactions without the consumption of calcium hydroxide, which increases the pH value. For the carbonated sample, a similar process occurs. However, there is a slightly consumption of calcium hydroxide, which lowers the pH value. Finally, with this paper, we can conclude the following. The usage of carbonated water in cement-based pastes produces a higher initial compressive strength until the curing age of 3 days. However, for the later ages, the compressive strength was lower than the reference sample. Results obtained from the compressive strength and X-ray diffraction indicated the promotion of the hydration reaction of cements. Regarding the pH results, there is a higher pH measurement for the curing age of 3 days when low carbonated water is used, occurring the opposite for the high carbonated water. There is also a stabilization of the pH measurements for the uncarbonated and carbonated sample for the later ages, similarly to the pH value occurring in uncarbonated concrete. This work was supported by the Polish National Agency for Academic Exchange, and the authors would like to thank them and also Ceres Research Center for the support. Thank you for your attention.